Welcome back to the second to last day of the 100 Days of Logic. Today we're going to be continuing with our final logic problem answers. These are going to be the answers to the expert problems. These problems were really hard. I counted it out. There are over 200 steps involved in solving these problems. That's a lot. That's crazy. I apologize if any of them are a little fuzzy in the video. They had to get really small for me to fit them all into the screen. If you were able to do these problems, honestly, if you were able to even do some of these problems, that's fantastic. You are a master of logic and should go on and do awesome logic things, because that's really cool. If you're able to do all of them, you should take my job, because that's amazing. Go make videos on YouTube and explain how you did it to other people. Fantastic. The problems we had, the first two, were as follows. I'm going to, so this video doesn't get too long, not read out everything in every single one of the problems. I'm just kind of explain the steps as I go through them. So, this was our first problem. There exists an x such that for all y, y bears relation a to x, or for all x, for all y, x bears relation b to y. There exists an x such that for all y, y is c implies that it's not the case that y bears relation b to x, and we're trying to conclude that for all x, there exists a y such that x is c implies that x bears relation a to y. Wow, that's a lot going on there. So the first thing I'm going to do with this problem is, because I don't have a nice implication, I don't really have anywhere good to start. I've got a disjunction and a really quantified statement. I'm going to go ahead and do an assumed indirect proof. So I'm looking for a contradiction somewhere eventually in this. I will deny my conclusion, and I'll draw my line going down. As you can tell, this is going to take a while. Then, because I can't do anything with the negation all the way on the outside, I'm going to do change of quantifier, not once, but twice. That'll move my negation inside, and it'll switch my two quantifiers from what they were to something else. Then we'll go ahead and instantiate premise 5, do both an existential and a universal instantiation on that, and we end up with, it's not the case that P is a C implies that P bears relation A to Z. It's from premise 6, universal instantiation. Note that I've left that Z, I haven't picked a specific variable, so I can later universal generalize that thing. Now we're going to do implication, because we're not able to work with our implication when there's that negation on the outside, and the only way we can bring the negation on the inside is to do De Morgan's, which we will do next to get a nice conjunction. Conjunctions are great because we can simplify them out to their component parts. We now have P as a C, and it's not the case that P bears relation A to Z. Great. Next, what we're going to do is we are going to take our second premise, and we are going to existentially instantiate it to get for all y, y as a C implies it's not the case that y bears relation b to n. Because we're using existential instantiation, we can't use any of the variables we've used before, so we're getting n. Next, we'll do universal instantiation. Because this is universal, we're allowed to use a previous variable. I'm going to pick p because, as you can see, it'll set up a nice modus ponens there between 10 and 13, which I will then, of course, do. It's not the case that p bears relation b to n, 10, 13 modus ponens. Next up, I'm going to go back to that premise that I simplified down to it's not the case that p bears relation a to z. I'm going to existentially generalize that. Then I will universally generalize that to get for all x there exists a y such that it's not the case that y bears relation a to x. Why would I want to do this, you may be asking? Well, what does this kind of look like? What part of our original premises does it look like? It should be clear that it looks like the first half of the disjunction in premise 1. For me to be able to use this disjunction in any important way, I'm going to have to deny one of the sides of it in order to use disjunctive syllogism and affirm the other side. Because I already have kind of a negation of B, that means that I may want an affirmation of B to get my contradiction eventually. So, because I have this kind of negation of A, the thing in the front, I'm going to use that for my disjunctive syllogism to end up with my B. If that didn't make sense, don't worry, I'm going to walk through the steps right now. So first we'll use change of quantifier twice to get that negation out on the outside, so we can use it with our first premise. Then we'll go ahead and do premise 118 disjunctive syllogism to get for all x and for all y, x bears relation b to y. Right now it should be clear where our contradiction is going to come from. If you look at 14 and 19, just reading those out, it should be clear that they are contradictory statements. One says there is a specific case where some p does not bear relation b to some n, while premise 19 says that for all things, they bear relation b to all other things. So if there were something that didn't bear that relationship to something else, that would entail a contradiction. Basically what that's going to mean is we'll do premise 19 universal instantiation for all y, p bears relation b to y, and then premise 20 universal instantiation, p bears relation b to n. We're allowed to do this and pick those variables we had before because this is universal, this is the general, this is not the existential or the specific. We then of course have bpn and not bpn from premise 14, premise 21 conjunction. That's a contradiction, so we can deny our original assumption in our indirect proof, which will give us the conclusion we were looking for. For all x, there exists a y such that x is c implies that x bears relation a to y. 3 through 22, indirect proof. Hopefully you're still on board. That was one of the easier ones. There's a lot of complicated stuff, and it would be really easy to get lost with the x's and the y's and the ways that they're shifting around here, because we do kind of use x and y over and over again. If you want to make it simpler, it would be okay to use like a w and a z as you're getting towards the conclusion to not confuse them with the x's and y's we had at the beginning. Anyway, moving on. Argument number 2 is going to go as follows. For all x, x is an I implies there exists some y such that y is a c and y is an a, implies that x is an e. Premise 2, there exists some x such that x is a t, or there exists some x such that x is a w, implies there exists some x such that x is an I, and there exists some x such that x is a c. Premise 3, for all x, x being a c implies that x is an a, and we're trying to get the conclusion of there exists an x such that x is a t implies there exists an x such that x is an I and x is an e. Looking at the conclusion, it should be pretty clear what our first step is going to be. We want to do a conditional proof here. It may be a little tough. The tricky part of this problem is going to be getting the same x to be with both I and e. Let's see if we can do it. The first thing we're going to do, assume conditional proof of the antecedent of our conditional. There exists an x such that x is t, and we'll draw our line going down. Then, because we can't do anything else to get w, and it's just placed in disjunction in premise 2, we're going to disjoin there exists an x such that x is w, and add that on to premise 4, which of course gives us the antecedent of premise 2, allowing us to use modus ponens on 2, 5 to get there exists an x such that x is I, and there exists an x such that x is c. We will then simplify that out to its 2 component parts, and then use existential instantiation twice to get p is a c and n is an I. We'll then go ahead and use premise 3. We'll universally instantiate that to get p is a c implies p is an a. We want to do that because we already have p is a c up in premise 9. We'll then use that and modus ponens to get p is an a. And then we'll conjoin 9 and 12 to get p is a c and p is an a. The reason we want to do that is we're moving slowly towards that kind of middle term in premise 1 because we're going to do a series of modus ponens to get that ex at the end because we eventually want that e. We already have the I existing, we want that e as well. So then we will existentially generalize to get it looking exactly like that middle term in premise 1. There exists a y such that y is c and y is a. Then we'll go ahead and take premise 1 and universally instantiate it. We will universally instantiate it to look like our I in premise 10 so that n replaces the x because we want there to exist an x such that it is both I and e, not existing an x that's I and existing another x that's e. We want them to be the same, so we need that n. Also, we wouldn't be able to do modus ponens if we didn't have the antecedent of the conditional in premise 15. Anyway, we will do that from 10, 15 modus ponens. We'll do another modus ponens to end up with n is ne, 14, 16 modus ponens. All that's left to do is now conjoin n as an I and n as an e to get pretty close to our conclusion. We now have there exists an x such that x is an I and x is an e. Premise 18, existential generalization, and we can close out our lovely conditional proof with there exists an x such that x is a t implies there exists an x such that x is an I and x is an e. 4 through 19, conditional proof. Whew! Thought that was long? We're just getting started. Now, we're going to move on to kind of the second level of problems. These are going to be our problems on identity. Take a look at this. I read it out in a previous video. I'm not going to do it again now because this video is already going to be pretty long. So, this is a really long problem, as you can judge by the fact that the print is pretty small. Honestly, there's not that many complicated or weird moves here. It's all stuff we've seen before. There's just a lot of it because you have to work through and simplify a lot out of these premises. It's the kind of thing, if you keep working at it, you'll get a sense of it. It is actually very similar in the way we're going to do this to problem number 4. If you had a lot of trouble with 3 and 4, I would suggest you watch this explanation and then try 4 on your own because we're going to use a similar method for both of them. Alright, so first we need to look at the conclusion. What are we trying to get? There exists an x such that there exists a y such that x is a fruit, x is in the tree, y is a fruit, y is in the tree, and it's not the case that x equals y. That's kind of the first half of our conclusion. And for all z, this is the second half, z is a fruit and z is the tree implies that either z is equal to x or z is equal to y. We're going to kind of have two halves of this proof. The first half is going to be worried about proving that first part of our conclusion. The second half is going to be worried about proving the second part of that conclusion. Let's take a look. First thing we're going to do is we can existentially instantiate premise 1. Get rid of all those existential quantifiers, and then we are going to end up with a nice long conjunction that we can break apart and do a lot of things with. The important thing here is we are going to be kind of naming our apples, as it were. We're going to be giving P the name to the apple that had X, and we're going to be giving Q the name to the apple that had Y. Eventually, at the very end of the proof, we're going to give them back X and Y, but not until we get to absolutely the very end. Until then, we're just going to have P and Q. We'll go ahead and simplify that long conjunction to a number of things we're going to need later. P is an A, Q is an A. It's not the case that P is the same as Q. And P is a T, and Q is a T, and it's not the case that P is the same as Q. Then we'll go ahead and universally instantiate our second premise twice so that we can use 6 and 7 with modus ponens to get P is an F and Q is an F. Fairly simple. Once again, we're just doing a lot of the same things over and over again. Then we will reconjoin these back with our original statement. Cool thing, we now basically have the first half of our statement. We haven't added the existential quantifiers on the front of it yet, but we don't want to do that yet. I'll show you why in a sec. What we're going to do now is we will start an assumed indirect proof. It might seem like we want to do a conditional proof here because you do see that conditional sign in the second half of our conclusion. However, that is going to be quantified over by that for all z. Because it's inside the kind of scope of that quantifier, we're not going to want to do a conditional proof because it'll run into that problem we talked about earlier with universal generalization and having a free variable in one of the first lines of your conditional or indirect proof. Anyway, the point is we are going to do an assumed indirect proof for the second half of our conclusion. The first thing we're going to do in our indirect proof is move that negation sign to the other side of our quantifier with change of quantifier, and we'll turn it into a there exists a z instead of for all z. Next, we're going to want to instantiate our variable z. Because we have existential instead of universal instantiation, we're going to have to come up with a new variable. Just like we kind of named our apple X and our apple Y, we're going to have to name our Z apple, this kind of possible third apple. We're going to call it R. Keeping with the order X, Y, Z, P, Q, R, it helps me remember it. You could have named it whatever you wanted in your proof, but I named mine R so I can kind of remember which correlates to Z, X, and Y. Anyway, we existentially instantiate, we end up with this negated implication. We know what to do with those. First, we'll use implication, and then we will bring our negation inside with De Morgan's law to use and end up with a lovely conjunction that we can then use simplification on to get R as an F and R as a T, 20 simplification, and also the other half simplified. We split it up nicely because we're going to need both of these statements later in our proof. Well, what are we to do now? Now we are finally going to be able to use that big, long, giant third premise. Because we've instantiated and kind of picked a name for apple X, Y, and Z, we can finally use that big, long chain and instantiate each of those universals to P, Q, and R. So that's the first thing we'll do. We'll instantiate for all X to P, so we'll replace all the X's with a P and get rid of our universal quantifier. We'll do the same with Y and Q, and finally the same with Z and R. We now have this lovely implication. If you look carefully at the antecedent, we actually have all of the parts of the antecedent already in what we've proven. We have, back up earlier in our proof, P is a fruit, P is in the tree, Q is a fruit, Q is in the tree, and we just recently proved that R is a fruit and R is in the tree as well. So, we'll go ahead and simplify 15 to get the first part of that, and we'll conjoin on the part we just proved in premise 21. This gives us the antecedent of that long conjunction, so we can conclude the consequent of that conjunction with modus ponens, 25, 27. Now what we're going to do is use disjunctive syllogism. We had all the way back in premise 8, we had, it's not the case that P equals Q. So we can use disjunctive syllogism to get rid of one of those kind of disjuncts in our long disjunction in premise 28. This ends up being Q equals R or P equals R. Now, at this point, if you look carefully, you should notice that premise 22 and this statement are actually a contradiction if conjoined. However, they're not perfectly exactly the same as each other, so it might be prudent to switch them around just to prove to someone and show to someone that they are the same. Premise 29, kind of the symmetrical rule of identity, twice will get us in almost the right place, and then we'll use commutativity to switch around the last bit so they look perfectly identical with the exception of negation. We conjoin 22 and 32, and we end up with a contradiction. This, of course, allows us to step out of our big, long, monstrous, indirect proof to end up with, for all Z, Z is a fruit and Z is in the tree, implies that Z is equal to P or Z is equal to Q. 16 through 33, indirect proof. We are almost ready to get to our conclusion. It's important to note that we don't have X and Y in this premise, nor do we have X and Y in the first half of our conclusion. That's important, because if we existentially generalized one half and then existentially generalized the other half, we would end up talking about two different things and we couldn't put them back together later. We have to put them all together and then existentially generalize over the whole thing. So that's what we're going to do. We will conjoin 15 and 34 to get our conclusion all together. Then we'll use existential generalization to replace all our Q's with Y's, and then existential generalization again to finally replace all of our P's with X's, doing the, as I said, last thing we needed to do, and ending up with our lovely conclusion that there exists an X such that there exists a Y such that X is a fruit and X is in the tree, and Y is a fruit and Y is in the tree, and it's not the case that X equals Y, and for all Z, if Z is a fruit and Z is in the tree, that means that either Z is equal to X or Z is equal to Y. Premise 36, existential generalization. QED. Wow, that's a lot of information. I'd suggest if you didn't follow it, pause the video, write some of that down, follow along or check your notes to see where you may have gotten lost. If you did follow it, that's amazing. Good for you. Next up, we had number 4. This is going to be a little less complicated, but a little bit of a longer proof. than the last one we did. Like I said, we're going to be using a similar technique, a similar style. So if you had trouble with 3, but now feel you have a better understanding of it, I would encourage you to try that kind of style of doing the first half of the proof, the second half of the proof, and then existentially generalizing over the whole thing at the end here. If you've already done that, or you're not comfortable and you want me to show you how, follow me and let's get started. So, this is our proof. Like I said, it's going to be longer. Whew. What we need to do is prove that there exists an x such that x is a p and x is an a, and for all y is a p and y is an a implies that y is x. So basically that there's only one thing that's both a p and an a. And we have a lot of premises to work with. What I would do first, to start us off, is to go ahead and simplify out some of these long strains of conjunction. First one we'll take a look at is premise 2. We'll simplify out kind of the important or the fun part of it, which is for all x is a p, and x is a t implies that x is j. Then we'll go ahead and do universal instantiation on this one. Our goal here is basically to show that through a series of proofs that f is not a t, or Fred is not a tiger. We'll use modus tollens, because 4 gives us it's not the case that f equals j. Then De Morgan's law. Then we'll go ahead and use simplification to get f as a p, so that we can then use disjunctive syllogism on 8, 9 to get it's not the case that f is a t. We're also going to simplify premise 1 down to it's not the case that f is an s. And then conjoin it's not the case that f is a t, and it's not the case that f is an s. 10, 11. Conjunction. Why were we doing all this, you may ask? Well, take a look at premise 3. Think equivalence and then modus tollens, and get back to me. So, we will then universally instantiate premise 3 to f, Fred. We will then use 9, 13, and modus ponens to get the second half of that implication, because we already had that Fred is a pet. Then we're going to split up that big old equivalence, because we remember that equivalence, that biconditional, that triple bar, splits into either 2 implications or 2 conjunctions, one being conjoining and one being conjoining the negations of the parts. We'll do it with the implications right here, so that we can then simplify, and then you note we have, ooh, look, the beginning of that implication. That was what we spent the first several premises getting. So that we can then prove that f is an a. Premise 12, premise 16, modus ponens. Why were we doing all of that, you may ask? Well, look at the first part of our conclusion. We're trying to get x is a pet and x is an a. If you read the problem, you understand that the only thing that is an a, that is adopted, is Fred. So we had to show that Fred was adopted. That took a lot of work, but we were able to do it. We can then conjoin, and we have that first part of our conclusion. Now, we're not going to existentially generalize, because as we did in the last problem, we need to wait until we have the second half of our conclusion. In order to get that, we are also going to be doing an assumed indirect proof. For the same reason as last time, we can't do a conditional proof, as that will mean there's a free variable in the first line of our conditional proof, and it'll mean problems for us universally generalizing later. We're not going to worry about that. We'll do an assumed indirect proof instead. Of course, we're going to have to do a change of quantifier to get that negation on the inside. And then we're going to come up with some other creature, we'll call him Bob, that we will existentially instantiate that to. It's important that we have a new variable because it's now existentially quantified instead of universally quantified. Now, we have the negation of an implication. Hopefully, by this point, we know what to do with that. We do implication, and then De Morgan's law, and we end up with this nice, juicy conjunction that we can then simplify into its 2 parts. We'll first simplify down to B is a P and B is an A, and then we'll simplify that in turn down to B is a P and B is an A. And we'll also simplify our original conjunction down to it's not the case that B is an F. Whew! That was a lot of simplifying that we just did there. Like I said, a lot of this problem is simplification. What we're going to be kind of shooting for eventually is getting something that can go into the second half of that first premise and get us that nice implication eventually. Let's see where we have to go to get there first. First, however, we're going to need to do our lovely implication trick with premise 3. So we'll universally instantiate premise 3. This time we're going to do it for B. Basically what we're trying to do is get a contradiction between B is an S and B is not an S. We will use modus ponens on this one because we already have that B is a P from 25 and we have the implication from 28. Then once again we'll end up with that long equivalence thing, but this time with B instead of F. We'll simplify it down, this time to the other part of the equivalence statement. That B is an A implies that it's not the case that B is a T, and it's not the case that B is an S. We will use modus ponens to end up with it's not the case that B is a T, and it's not the case that B is an S. Simplify that down to it's not the case that B is a T, and it's not the case that B is an S. Remember that it's not the case that B is a T is kind of what we were looking for earlier, and that it's not the case that B is an S is going to be the thing that we're going to use for our contradiction. So, now we have to, in order to finish all of the things that we have in that kind of second part of the first premise so that we can show that B is an S and also not an S, therefore a contradiction, we're going to have to get, it's not the case that B is a J. So we're going to assume indirect proof. This is where that it's not the case that B is a T is going to come in handy. J is a T, that's just premise 2 simplification. B is a T, that's going to be identity with 3536. And then we will end up with a lovely contradiction. B is a T and B is not a T. So it's not the case that B is a J. It may have seemed like our indirect proof was over there because the line stopped. It's not. I just had to take a little bit of a break between that line because premise 15 was so long. Our indirect proof is continuing below. Premise 40, we're going to go ahead and start conjoining things. Once again, we are looking to get the first half of the second part of premise 1. We will conjoin all these lovely things that we've discovered. We'll simplify premise 1 down to that first part that we've been working so hard towards. We will universally instantiate premise 42 so that B replaces all of our X's. It should now be clear that the first part of that premise looks like all the things we just conjoined from all the different things we were doing here. Eventually, we will get B is an S, modus ponens, and we can conjoin B is an S and B is not an S to get a contradiction. Ah, a contradiction. We can finally jump out of this very long indirect proof that we've been doing. So we get for all y is a P and y is an A implies y is F. From premise 19 through 45, indirect proof. Now all we have to do is join this up with the first part of our argument. We'll conjoin them together, and finally we will existentially generalize over the whole thing, replacing all of our F's with X's, and end up with our conclusion. Whew! Wow, that was long. The good news is that's the longest of all the proofs in this expert series. The other ones are only tough because they use kind of some modal language and things like that. Let's take a look. Number 5. This is going to be significantly shorter than the last couple problems that we've done, or at least shorter than the last problem that we've done. It's just going to be a little bit more complicated because it has the kind of necessity and possibility ideas floating around, and if you're not so comfortable with those, you should watch my video on modal logic. Let's take a look. So, it should be clear that this should be one long conditional proof. We have an implication as our conclusion, so we're going to want to do a conditional proof. That's how we will start it off. C is an A. Beginning of a great conditional proof, and our line will go down for a while. Now, the other important thing you should notice about the premises is there is already a contradiction kind of hidden amongst the premises. And if you didn't notice it, you might spend a lot of time kind of trying to do a lot of things that aren't going to get you anywhere. Note that the second part of premise 2 is, it's not the case that it's possible that P is R, and for all x, x is R. If it's not the case that some P is R, and for any x, x is R, that's not going to work together. That's going to be a contradiction. So let's go ahead and prove that that's a contradiction. We will assume that it is the case and show it leads to a contradiction, so we can deny it and use modus tollens on premise 2. We'll simplify it out to, it's not the case that it's possible that P is an R, and for all x, x is an R. We will then use change of modal quantifier on premise 6 to get it's necessary that it's not the case that P is an R, and then it's not the case that P is an R. Premise 8, axiom M. We'll universally instantiate premise 7 to get P is an R, and we will conjoin them to get a contradiction. Therefore, we can deny everything that we just stated up in premise 5, and we will be able to conclude it's not the case that there exists an x such that C bears relation B to x from 2, 12 modus tollens. This, in order to work with it, we have to use change of quantifier, so we'll bump that negation sign inside the for all x. And then what we're going to do is we're going to do another assumed indirect proof. Why are we going to do this? Well, if you look carefully at the second part of premise 1, once again, you should see something that's contradictory with what we just proved. So, putting those together, we should end up with a contradiction and be able to once again use modus tollens and deny backwards up premise 1. So, we will assume the consequent of premise 1, for all x there exists a y such that x is an A implies that x bears relation B to y, assumed indirect proof. Then, we will get, there exists a y such that C is an A implies C bears relation B to y from 15. Universal instantiation. We've instantiated to that C because that C is going to be useful for us. And then we will finally existentially instantiate with a new variable S to get C is an A implies C bears relation B to S. We can then get BCS from 17 modus ponens. You see we already have AC all the way back in the beginning of our assumed conditional proof. So we get BCS. We can also get not BCS. How? If we universally instantiate premise 14. It was a good thing we did the existential instantiation first, so that we could then use the universal instantiation to pick out whatever variable we grab with the existential instantiation. We have, it is the case that BCS, and it's not the case that BCS. That's a contradiction, so we can step out of our indirect proof to get, it's not the case that for all x there exists a y such that x is an A implies that x bears relation B to y. 15 through 20, indirect proof. The denial of that allows us to run backwards up premise 1 and deny with 121 modus tollens the first half of premise 1. So it's not the case that it's possible there exists an x such that it's not the case that it's necessary that x is a d, or it's not the case that it's necessary that x is an e. Wow. We're going to do some change of quantifiers. First we'll do a change of modal quantifier, then we'll do a change of normal quantifier. We'll end up with it's necessary that for all x and all the things that I just said before. Then we're going to, because we have that negation on the outside, we're going to do De Morgan's to bring it inside. I don't know why in this proof I decided to have to use double negation. I just did. You don't have to. I haven't been for the other proofs, so don't really worry about it. We'll use double negation twice to get ourselves to this lovely statement. We can then use axiom M to get rid of that necessary in the front of our statement. It's not really necessary for us anymore. Then we will go ahead and universally instantiate. We will universally instantiate to C again. Why will we universally instantiate to C, you may ask? Because we are trying to get to the first half of premise 3 so we can finally get that implication and send that over to ZC, which is our eventual goal. We universally instantiate. Then, because there's no other place for us to get this C as an F, we're going to have to add it on with a disjunction. But that's okay, because it's disjoined in the actual premise. So we will disjoin, it's necessary that C is an F. We'll then use distribution to split that up and pair that with both the C is a D and the C is an E. Then we're going to kind of have to pull all of these necessary signs we have out of the spots that they are. With our modal distribution rule, we'll pull them out 1, 2, 3 times to get our necessity all the way on the outside. Now you might think at this point you are allowed to use modus ponens and finish it up, but not quite. Look carefully at premise 3. You will see that the necessary covers all of the premise. It covers the C is a Z as well. So we can't use it quite yet. We have to do one more thing. We have to use modal distribution on premise 3 to split that necessary up. We can then conclude C is a Z from modus ponens with the rule we just used, as well as adding in axiom M to reduce the necessary that C is a Z down to just C is a Z. I skipped that step. It's not terribly important. And finally, we will get C is an A implies C is a Z from 4 through 36 conditional proof. Whew! That was a lot to do. Because this video is growing way, way too long, I'm going to stop us here and do a separate video, don't worry, it'll also be posted today, on the modal perfection argument, the last of our problems for the expert level. Because it's a little bit different, it doesn't use all of the skills that I've taught you. So, stay skeptical, everybody, and stay tuned for that video.